Hello, this is a group presentation for the course EME 521. My name is Dana, and today my team and I will cover the topic of the Lattice-Boltzmann method, or the LBM for short. To give a brief outline, we'll go over the introduction, historical perspective, core principles, and governing equations, and then we'll go over some examples, both hand-calculated and numerical, to show its practical applications. We first need to understand what Lattice-Boltzmann method is and why it's important. To put it simply, the Lattice-Boltzmann method is a numerical method that simulates fluid dynamics on a macroscopic scale based on kinetic equation formulated on a mesoscopic scale. The fluid is represented as a discrete particles. Each particle follows a velocity distribution function defined at every grid point, allowing for an accurate modeling of fluid flow. The LBM is widely applied in computational fluid dynamics. One of its primary uses is solving the Boltzmann transport equation, which helps in predicting the complex fluid behavior in engineering and scientific simulations.
In this section, I'll walk through the general principles behind LBM and how it fundamentally differs from traditional fluid dynamic approaches. As stated previously, LBM is a computational technique for simulating fluid flow. Fluid flow occurs across multiple scales. Traditional computational fluid dynamics, or CDF, solves for quantities like velocity and pressure at every point in space using continuum equations. This involves directly solving macroscopic Navier-Stokes equations. However, solving the Navier-Stokes equations analytically is difficult for several reasons. First, they include nonlinear convective term, meaning the rate of change of velocity depends on velocity itself. Nonlinear equations are inherently challenging because small changes in input can lead to large unpredicted outcomes. Additionally, the Navier-Stokes equations are a set of coupled partial differential equations with components in the x, y, and z directions. These components are linked through the pressure and velocity fields, so solving one equation typically requires knowing the solution to the others. Finally, boundary conditions. Navier-Stokes struggles with curved and moving surfaces, and geometric complexity makes analytical solutions nearly impossible outside of ideal cases. On the other end of the scale is molecular dynamics, MD, which simulates physical movement of atoms and molecules over time by solving Newton's equations of motion. Each atom or molecule is modeled as a particle with a mass, position, and velocity, and the forces between them are determined by interatomic potentials. While MD offers high physical fidelity, it is computationally expensive and limited to very short timescales and small systems. LBM sits between MD and continuum models. It operates at a mesoscopic scale, tracking probability distribution functions for particles at each node on a grid. These particles stream and collide according to simplified kinetic rules. LBM can be viewed as the statistical model that simplifies molecular dynamics by grouping particles and replacing deterministic forces with probabilistic interactions. This approach alleviates many of the computational challenges faced by both MD and continuum models while still capturing essential fluid behavior. To build the full picture of LBM from first principles, we begin by examining the Lattice-Boltzmann equation without collisions. At its core, the LBE governs the evolution of particle distribution function at each node on a discrete grid across specific timescales and directions. In the collisionless case, there is no mechanism for momentum or mass exchange between directions. As a result, the system lacks relaxation effects, meaning it cannot exhibit realistic fluid behaviors such as viscosity, nor will it ever reach equilibrium. While this setup is not physically accurate for modeling fluid, it serves as a useful role in code implementation by separating the streaming step from the collision step. The concept of particle motion and the use of the lattice comes from the lattice gas automata, but LBM replaces the discrete binary particle tracking of LGA with a smooth statistical approach. Rather than following individual particles, LBM tracks the average particle distribution in each direction. Collisions between these distributions enable momentum exchange, pressure propagation, and shear, while also conserving mass and momentum locally. In essence, the Lattice-Boltzmann method models how many particles are moving in each direction at each point in space. These distributions evolve through two main steps, streaming and collision. When implemented properly, this bottom-up statistical approach can effectively reproduce the behavior of real fluids. LGA transitions into LBM through the introduction of a distribution function. In LGA, fluid flow is simulated using discrete particles moving on a discrete lattice at discrete time steps. Each particle moves in a fixed direction on the lattice and interacts with other particles via simple, predefined collision rules. The occupancy variable Ni is a Boolean function of position, time, and direction, indicating whether a particle exists in direction I at a given site and time. The collision rules in LGA are designed to conserve mass and momentum, and the result after a collision is reproduced by Ni star is the post-collision Boolean state. To evolve from LGA to LBM, we replace the Boolean particle state with a real value distribution function, Fi, which represents the average number of probability of particles at a given location and moving in a direction. When this distribution function is incorporated into the LGA framework, the system begins to resemble the LBA formulation. To compute the model, we introduce an equilibrium distribution function, FIEQ, which defines the state towards which the system relaxes. Additionally, a relaxation parameter, omega, is included to control the rate at which the system returns to equilibrium after the collisions. The right-hand side of the LBM equation thus includes both the equilibrium condition and the relaxation adjustment, effectively replacing the deterministic logic of LGA with a smooth statistical relaxation mechanism. The LBM algorithm starts with initializing the simulation domain. This means defining a discrete lattice such as D2Q9 or D3Q19. Initial values are assigned for the distribution function as well as the macroscopic quantities like density and velocity at each node. For these, the equilibrium distribution functions are calculated. The simulation then progresses in a loop of discrete time steps. In each step, particles start by streaming along their lattice directions to neighboring nodes in the streaming step. Boundary conditions are then applied to handle interactions at walls, inlets, outlets, or periodic edges. After streaming, the boundary enforcement, the macroscopic quantities like density and velocity are recalculated at each node by taking moments of the distribution function. These quantities are then used to recompute the equilibrium distributions. In the collision step, the distribution functions are relaxed towards equilibrium using a collision operator, which models local interactions and viscosity. This process, streaming, boundary application, macroscopic reconstruction, and collisions, is repeated over many time steps, allowing the flow field to evolve. Once the simulation reaches convergence, or the final time, the results are extracted in the form of velocity fields, pressure distributions, and other macroscopic flow properties. LBM is a versatile and increasingly widespread tool. In fluid dynamics and aerospace engineering, LBM is used for aerodynamic modeling, offering advantages in handling complex geometries and unsteady flow conditions. It is also well suited for simulating multi-component and multi-phase flows, making it valuable for studying interactions between gases, liquids, and solid boundaries. In biomedical engineering, LBM has been employed to simulate blood flow through arteries and capillaries, capturing detailed flow parameters that are critical for understanding circulatory health, as well as aiding in the design of drug delivery systems and medical implants. LBM is also used in energy and thermal systems. It provides insight into combustion dynamics, helping researchers analyze flame propagations and energy release in reactive flows. Its ability to handle heat transfer in complex domains also makes it useful in optimizing the performance of cooling devices such as heat exchange and electronic cooling systems. In environmental science, LBM has proven useful for modeling the dispersion of pollutants in air and water, as well as simulating soil absorption processes. Its strength in capturing liquid flow through porous media has made it a valuable tool in the study of hydraulic fracking and in assessing the feasibility and efficiency of underground carbon sequestration strategies. LBM has found application in soft matter physics where it is used to model phase separation, the dynamics of foams, and the behavior of colloidal suspensions. Its ability to represent interfacial dynamics and complex fluid interactions at the mesoscopic scale makes it especially suitable for these systems. Over the last 30 years, LBM has experienced remarkable growth in both adoption and application. In fact, in 2020, an entire study was dedicated to analyzing the frequency of LBM's appearance in scientific literature. This meta-analysis focused on publication trends in three major regions: China, the United States, and the United Kingdom, and it traced the related work back to its origin to 1988. According to their findings, LBM appeared in over 1,200 separate publications in 2018 alone, solidifying its place as one of the most widely used dynamic simulation techniques. Given its simple implementation and the recent surge in computational interest, the increasing popularity of LBM is not surprising. What's most impressive about LBM, however, is its publication success across a wide range of disciplines. According to the same study, the field with the highest number of LBM-related publications include, in order, mechanics, physics and mathematics, fluid physics, computer science, interdisciplinary applications, thermodynamics, mechanical engineering, multidisciplinary physics, chemical engineering, physical chemistry, material science, and general multidisciplinary areas. The diverse fields highlight LBM's adaptability and relevance across both theoretical and application research domains.
Let's take a closer look at the governing equation behind the Lattice-Boltzmann method, or LBM. LBM is essentially a discretized version of the continuous Boltzmann transport equation, the BTE. Instead of following individual particles, it models the evolution of distribution functions, which represent how particles are spread across space and velocity at a given moment in time. This approach works at the mesoscopic scale, sitting between microscopic molecular detail and macroscopic fluid behavior. The core object in this formulation is the distribution function f, written as f of x v t. This notation tells us how many particles are present at a specific position x, moving with velocity v at time t. You can imagine this like a fog of particles moving through space, and f measures how thick that fog is, but not just in space, also in velocity. So for every point in space and every velocity, we know how populated it is. The molecular density is quantified by the expression F over dr dV. Here n is the number of particles inside a tiny region of space, and velocity. The dr term refers to a small volume element in space, a tiny cube for example, and dV is the small region of velocity space we are considering. Altogether, this gives us the number of particles per unit volume in both position and velocity space. That's what makes F a distribution. It's not just about where particles are, but also how fast they are moving and in which direction. Now, let's talk about how F changes over time, its time evolution. As time advances from t to t plus delta t, every group of particles or every cloud point in the distribution experiences three changes. First, particles move through space. If they are traveling with velocity v, they shift by v times dt. Second, they might be acted on by external forces, gravity, for example, which alters their velocity. This acceleration is represented by a, and over a small time dt, the velocity changes by a times dt. Third, of course, time itself moves forward. So altogether, the distribution evolves like this. F of x vt becomes f of x plus v dt, v plus a dt, a times dt, and t plus dt. Now, let's look at how space is structured in the Lattice-Boltzmann method. In LBM, space is discretized into several regular Cartesian lattices, structured grids where each node represents a point in space and connects to its neighbors through a fixed set of directions. This discretization is what allows the continuous physics of the Boltzmann equation to be implemented in a computationally manageable way. Each lattice structure in LBM is denoted using the format DDQQ, where the capital letter D is the number of spatial dimensions and Q is the number of discrete velocity directions available at each node. For example, D2Q9 refers to a two-dimensional lattice with 9 discrete velocity directions, and D3Q19 refers to a three-dimensional lattice with 19 discrete directions. In the D2Q9 model, which is commonly used for simulating 2D flows, each lattice node has 9 possible states. One of them is stationary, the particle does not move. 4 directions represent movement along the cardinal axis: up, down, left and right, and the remaining 4 allow diagonal movement. This set captures essential 2D dynamics while keeping the model simple and efficient. In 3 dimensions, the D3Q19 model expands the number of velocity directions to 19. It includes 1 stationary state, 6 directions aligned with the Cartesian axis, forward and back, up and down, left and right, and 12 directions along the face diagonals of the cube. This richer set of velocities allows for a better approximation of 3D fluid motion while maintaining computational efficiency. In the Lattice-Boltzmann framework, particles aren't tracked individually. Instead, they are imagined to reside on the nodes of a structural lattice. Each node connects to its neighbors via a set of fixed directions, and along each of these directions particles can stream and collide. These directions are defined by velocity vectors commonly denoted I E. For instance, in the DQQ9 model, there are 9 such vectors, each representing a distinct path a particle can follow. The heart of the method lies on the Lattice-Boltzmann equation, which governs how particle distribution functions evolve over time. Mm, This equation represents two major processes. On the left-hand side, we have streaming, the advection of particles along their discrete velocity directions. On the right-hand side, we see collision, where the particle distributions interact locally and relax toward equilibrium. Each distribution function, fxt, describes how many particles are moving in a particular direction at a point x and time t. Unlike macroscopic quantities like velocity or pressure, these functions operate at a finer directional level. They are the building blocks from which macroscopic fluid behavior eventually emerges. This is the discretized form of the Lattice-Boltzmann equation tailored for numerical simulation. On the left-hand side, we see the propagation step, also known as streaming. The distribution function fi at position x moves along the discrete velocity direction el, reaching a new position x plus e after a time step delta t. The difference between the new and current values of fi represent the net streaming effect. On the right-hand side is the collision term, which governs how particle distribution locally relax toward equilibrium. This two-part structure, one term for motion, one for interaction, is the basis of how LBM captures fluid behavior in a step-by-step computable way. This equation introduces the BGK collision operator named after Bhatnagar, Gross, and Crook. It models how the particle distributions Fi relaxes toward an equilibrium state FIEQ over a characteristic relaxation time tau. On the left side is the same streaming step as before, and on the right, the collision is expressed as a relaxation process, the, the current distribution minus the equilibrium scaled by tau. The equilibrium function FIEQ is shown below. It depends on the local density ρ, the macroscopic velocity vector u, and the direction vector el. This expression ensures the method reproduces correct fluid behavior, capturing momentum and energy transport. Constants like Cs, the lattice speed of sound, and Wi, the lattice weights, are tuned to maintain consistency with the Navier-Stokes equations. As we mentioned before, the Lattice-Boltzmann method can be built on many different lattice configurations, but not all of them are physically valid. To ensure that the method correctly reproduces the desired macroscopic fluid equations, the chosen lattice must satisfy set of mathematical constraints. These include conditions on the weight, Wi, which ensure mass conservation, symmetry conditions on the velocity vectors, Ci alpha, which eliminates spurious momentum, and higher order moment constraints that help recover the correct pressure and stress behavior. For example, the second moment condition ensures that the model captures isotropic pressure through a relationship involving the lattice speed of sounds Cs and the Kronecker delta. These symmetries are what allow the microscopic rules of LBM to yield accurate macroscopic fluid dynamics. For the D2Q9 lattice configuration, for example, the weighting factors Wi assigned to each velocity direction are grouped based on symmetry. 1 for the rest vector, 4 for the short cardinal directions, and 4 for the diagonals. These weights are determined by solving the system of constraints involving the speed of sound, Cs, ensuring that the model reproduces correct fluid behavior. The solved values are shown here with the rest direction carrying the highest weight. Below we define how macroscopic fluid properties like density, rho, and momentum rho are computed by summing over the distribution functions and their velocities. Lastly, the fluid's kinematic viscosity is expressed in terms of the lattice spacing, time step, and relaxation parameter tau, linking the microscopic model back to observable physical properties. In summary, the Lattice-Boltzmann method models fluid behavior using discrete distribution functions Fi that evolves through streaming and collision steps across a lattice. The evolution is governed by the Lattice-Boltzmann equation, often with the BGK approximation for collisions. The method relies on well-designed lattice structures like D2Q9, which must satisfy specific symmetry and moment conditions. Macroscopic variables such as density, momentum, and viscosity are recovered by summing over these directional distributions, linking microscopic updates to fluid scale dynamics.
Now, I'll guide you through a clear, intuitive walkthrough of LBM method using a hand calculation. We'll go beyond numbers, seeing how simple, local actions like collisions and streaming build up to realistic heat transport. Along the way, I'll explain why each step matters, highlight common pitfalls, and connect everything to broader applications. Imagine a simple 5-meter long channel. Initially, the entire channel is at 300 Kelvin. At time zero, we instantly raise the temperature at the inlet to 400 Kelvin, while a fluid flows through the channel at a constant speed of 0.1 meters per second. Now, the equation that normally governs this system includes the time rate of change of temperature field plus the flow speed times the spatial rate of change of temperature, equaling to the thermal diffusivity times the second spatial derivative of temperature. Instead of solving that directly, we're going to model fluid behavior using discrete packets that move and relax on a grid. These packets allow us to capture both advection, or direct movement, and diffusion, or spreading out, without solving any partial differential equations. To keep it manageable, we use just 5 nodes, 1 per meter. This coarse grid lets us manually track every operation. While not realistic for real simulations, it clearly shows the core mechanics. Think of each node as a container of particle distributions that collide and stream at each time step. Before any physics happens, we set our initial and boundary conditions. We map physical variables to dimensionless ones. For distance, we map x prime equal to x divided by 5, which is our total length. For time, we map t prime equal to t divided by 4 hours, which is our total time. And for temperature, we map uppercase T prime equal to phi minus 300 divided by 100. At time equal to 0, every node has a temperature of 0. So for all of the distribution functions, they equal 0. At node 1, we immediately impose a temperature equal to 1, which is our thermostat, by setting F minus 1, F0, F1 equal to 0, 0, 1. This simple array assignment defines the entire subsequent evolution. Normalization ensures stable, accurate computation and helps us see parameters roll clearly. Our non-dimensional parameters become u prime equal to 0.1 meters per second times 4 hours divided by 5 meters, which is roughly 0.08, and alpha prime equals 0.25 meters squared per hour times 4 hours divided by 5 meters squared to become 0.04. By choosing the delta x lattice and the delta t lattice to equal 1, each time step of our simulation corresponds to 1 physical hour. Here's the 5-step loop we'll repeat for each hour of our hand calculation. Each step corresponds to a concrete operation we'll carry out manually at each node on our grid. At time t prime equals 0, we start by assigning values to the distribution function at each of the 5 nodes. Nodes 2 through 5 begin with 0 temperature, which means all of their distribution functions are also 0. In other words, those nodes are empty and have no thermal energy. Node 1, on the other hand, represents our heat source. It starts with all the energy, so we set the distribution function moving to the right, f sub 1, and we set it equal to 1. The resting component, f sub 0, and the left moving component, f sub 2, are both set to 0. This setup corresponds to a temperature of 1 at the inlet and 0 everywhere else. While in code, this would be just a simple array assignment. In our hand calculation, this step defines the initial state from which everything else evolves. It embeds the thermostat at the inlet and gives us a clear baseline for tracking how energy spreads across the domain. To compute the equilibrium distribution function FIEQ, we combine the local temperature T prime with the flow bias term. This bias is calculated as the dot product of CK and U prime divided by the square of the speed of sound. The weights used are W and T. When I is 0, W is 4 divided by 6, and when I is plus or minus 1, it equals 1/6. These weights to determine the likelihood of a particle resting, moving to the right, or moving to the left. FEQ equals the weight times T prime multiplied by the quantity 1 plus the dimensional bias, which is 3 times the velocity component in that direction. This formula adjusts the particle distribution based on both temperature and flow, capturing static diffusion and directed advection in a single step. The BGK collision step updates each distribution function using a relaxation formula. The new value, F star I, is equal to 1 minus omega times the current value of Fi plus omega times the equilibrium rate, FIEQ. In our case, omega is set to 0.8. This parameter controls how likely the distribution gets there past and moves towards equilibrium. A higher value of omega leads to faster relaxation, which means stronger diffusion. a lower omega slows the progression down and preserves sharper gradients. This step is entirely local. It does not rely on values from neighboring nodes and represents the effect of many microscopic particle collisions occurring within each grid cell. Streaming is literally a data shift. It moves F1 to the right and F2 star to the left and leaves F0 star in place. In practice, this is a memory copy across grid indices. Physically, streaming represents free flight between collisions, carrying thermal energy downstream and smoothing it across adjacent nodes. After streaming, we reimpose. Inlet, or node 1, resets F1 to maintain T prime equal to 1, simulating an ideal thermostat. Outlet, node 5, reflects outgoing packets enforcing zero flux, which is an insulated end. Then, summing Fi gives T prime at each node. This simple add operation recovers the temperature field, which we can plot or analyze. Finally, our output are dimensionless values that can be remapped back to temperature. We'll repeat this full loop for each hour in the hand calculation, updating values step by step across all 5 nodes. Because everything is local and rule-based, it's possible to carry out the entire process by hand while still capturing key physical effects like diffusion and advection. Our final output for our hand calculation will be the temperature across a 5-meter channel after 4 hours. In one dimension, the simplest lattice is D1Q3, 3 velocities, -1, 0, +1. Although minimal, it perfectly captures the physics of advection, diffusion in 1D. The weights W sub 0 equal to 4/6 for stationary packets and W sub +1 or -1 equal to 1/6 for moving ones satisfy key movement conditions, ensuring mass conservation and setting the effective speed of sound equal to 1/3. These choices aren't arbitrary. They anchor the lattice to reproduce the correct diffusion rate. At time equal to 0, all nodes have temperature equal to 0, so Fi equals 0 everywhere except the inlet, where F1 equals 1. The relaxation parameter omega is derived via Chapman-Enskog expression to link lattice collisions to macroscopic diffusivity. Explicitly, F-1, F0, and F1 equals 0, 0, and 1 at node 1 and 0, 0, 0 everywhere else. This initialization places hot particles at the inlet ready to stream. Each iteration we enforce F1 of 1 equals the temperature of the wall minus F0 of 1 minus F-1 of 1, which ensures that the inlet remains at temperature equal to 1. Think of this as an ideal thermostat that instantly corrects any drift. After computing equilibrium distributions, we find that at node 1, FEQ is approximately equal to 0.66, 0.26, and 0.16. Collision then yields F star approximately equal to 0.53, 0.37, and 0.09. These numbers reflect the mix of rest and flow bias packets moving towards a local Maxwellian distribution. In the streaming step, F1 star hops to node 2, while F-1 star would hop out of the domain it reflects back in and F0 star stays put. We then reapply the inlet thermostat and reflect at the outlet, preserving energy and enforcing physical constraints. Following streaming and boundary enforcement, our lattice has new Fi values at each node, ready for macroscopic reconstruction. At time equal to 1 hour, we can sum the distributions, which gives us temperature of T equal to 1, 0.37, 0, 0, and 0. Mapping this back to real values yields 400, 337, 300, 300, and 300 Kelvin at nodes 1 through 5. Node 2 has begun to warm, illustrating how the heat front emerges. In the second hour, we repeat equilibrium and collision, where node 2 FEQ increases due to incoming hot packets, then F star mixes towards that equilibrium. Streaming pushes these warmer packets into node 3, and boundaries are reapplied. At each step, the balance of advection and diffusion shapes the temperature profile. Now, after 2 hours, the temperature equals 1, 0.46, 0.13, 0, 0, and mapping it to real temperatures, we get 400, 346, 313, 300, and 300 Kelvin. You can see node 3 warming, highlighting the front's progression. The third collision steps further relaxes distributions. Node 3's packet approaches their local equilibrium, influenced by both inlet heat and upstream collisions. Streaming carries heat into node 4, with the outlet still insulated. This careful enforcement prevents non-physical leakage. Summation yields temperature equal to 1, 0.53, 0.20, 0.05, and 0, corresponding to 400, 353, 320, 305, and 300 Kelvin. The heat front visibly moves deeper. In our final hour, equilibrium distributions reflect the accumulated history. Collisions and streaming act one last time to spread heat into node 5. Streaming completes the final hop. Boundary conditions ensure conservation and maintain inlet heat. And finally, now that time equals 4 hours, our temperature equals 1, 0.59, 0.27, 0.09, and 0.01. Mapping to real temperatures, we get 400, 359, 327, 309, and 301.9 Kelvin. This sequence of local operations has captured the complex interplay of advection, bringing heat downstream, and diffusion, spreading it out.
Now we will go over a numerical calculation.
We're simulating a two-dimensional rectangular domain that's 80 meters wide and 120 meters tall. At the start of the simulation, the entire domain is set to a uniform temperature of 0. At time 0, we instantaneously heat the left boundary to a constant temperature of 1. That boundary stays at 1 for the entire simulation. The top boundary remains fixed at temperature equal to 0. The bottom and right boundaries are insulated, which means no heat can enter or leave through them. This is called adiabatic or zero flux boundaries. Inside this domain, a fluid flows steadily with a velocity of 0.15 meters per second in the horizontal direction and 0.1 meters per second in the vertical direction. The porous material has a thermal diffusivity of 0.8 square meters per second, which determines how fast heat spreads out throughout the medium. Our goal is to simulate how temperature evolves over time, and in particular, we'll analyze the temperature distribution at two snapshots, 100 seconds and 200 seconds.
The simulation involves 5 major steps: initialization, collision, streaming, application of boundary conditions, and finally updating the macroscopic temperature. During initialization, we define the size of the domain and set the initial values for the temperature and the distribution function. We use D2Q9 lattice model, which involves 9 discrete directions. The weight function for the directions 1 to 4 are 1/9, and the directions 5 to 8, which are the diagonals, the weight is 1/36. The relaxation parameter omega is calculated based on the lattice sound speed CS, which equals 1 divided by the square root of 3. The parameters control how quickly the system relaxes towards equilibrium. Now let's look at the first key operation that powers LBM, collision. This step models local relaxation, meaning that at each grid point the distribution function gradually adjusts towards its equilibrium. The distribution function is written as Fi and its equilibrium counterpart is FIEQ. The update rule for the collision step is a simple weighted average. The new value of the distribution function equals 1 minus omega times the current value of F plus omega times the equilibrium value of FEQ. For example, in the code this is written as F of ij and all directions equals 1 minus omega times F of ij plus omega times FEQ of ij. To calculate this equilibrium distribution, we use both the local temperature and the velocity components of each grid point. So for one of the directions, let's say direction 1, the equilibrium distribution is calculated like this. You take the weight from direction 1, multiply it by the temperature at the grid point, and then multiply the correction factor based on flow. That correction factor is 1 plus 3 times the horizontal velocity at that point. Thus, the equilibrium distribution in direction 1 equals the weight in direction 1 times the local temperature times the quantity 1 plus 3 times the horizontal velocity. We use a similar formula for all of the other directions and adjust based on their representative velocities.
Next comes the streaming step. This step moves each part of the distribution function to the neighboring grid cell following its direction of motion. You can think of this step as physically shifting little packets of heat across the grid. In the code, this is done using a circular shift function. Let me explain with a couple examples. For direction 1, which points to the right, we shift the data by +1 in the x direction and 0 in the y direction. For direction 2, which points upward, we shift by 0 in the x direction and +1 in the y direction. We continue for all the other directions, left, down, and all 4 diagonals. Each direction corresponds to a specific shift that mimics how particles move in space. Together, these two steps, collision and streaming, allow us to simulate complex thermal transport using only local updates.
Handling boundary conditions correctly is one of the most important parts of any LBM simulation. In our case, we apply 2 types of boundary conditions, Dirichlet and Newman. The left boundary of the domain is a Dirichlet boundary, which means that the temperature is fixed at a constant value, in this case 1.
In the LBM framework, we don't assign this temperature directly. Instead, we reconstruct the incoming distribution functions so that they correspond to the desired temperature. To do this, we use the equilibrium weights, the known wall temperature, and the outgoing values from the interior of the domain. For example, we say that the incoming distribution in direction 1 at the left edge is equal to the weight for the direction times the wall temperature plus the weight for direction 3 times the wall temperature minus the outgoing distribution in direction 3. This combination ensures that the macroscopic temperature at the boundary remains fixed at 1. Now let's move to the top boundary, which is also a Dirichlet condition, but with a fixed temperature of 0. Since there is no thermal energy coming in from this boundary, we reflect the outgoing particle distribution back into the domain with a minus sign. This creates a situation where the incoming energy is effectively 0. So, for instance, the incoming distribution in direction 7 is set equal to -1 times the outgoing distribution in direction 5. That negative reflection ensures that the net incoming energy is cancelled, maintaining a boundary temperature of 0. The bottom and right boundaries are treated differently. These are Newman conditions which correspond to insulated or adiabatic walls. That means no heat is allowed to pass through these boundaries. In LBM, we implement this using reflection. This simply means that the incoming particle distribution is set equal to the outgoing distribution from the corresponding neighboring cell moving in the opposite direction. At the bottom boundary, for example, the incoming value in direction 2 is taken from the outgoing value in direction 4 in the cell directly above. On the right boundary, the incoming value is direction 3 is taken from the outgoing value in direction 1 from the cell directly to the left. These reflections ensure that there is no net energy transfer across the boundary, which enforces the zero flux condition. By carefully designing these boundary interactions using the Dirichlet reconstruction for fixed temperatures and reflection for insulated walls, we preserve both physical realism and numerical stability throughout the simulation. Now let's examine the simulation results. This page shows the temperature distribution along the horizontal center line of the domain, that is, the line that cuts across the domain at mid-height. At both 100 seconds and 200 seconds, we can clearly observe how heat has diffused and been carried by the fluid from the hot left boundary towards the right side. Over time, the peak temperature moves further into the domain and the curve becomes more spread out, indicating combined effects of diffusion and advection. This slide shows contour plots of the full temperature field at different times. On the left side, the x direction velocity is dominant, which causes the temperature contours to stretch more horizontally. Heat is manually transported from left to right, and the vertical movement is weak. This means that in the vertical direction, diffusion dominates. In contrast, on the right side of the slide, the y direction velocity is stronger than on the x direction. Here, the contours are tilted upward, showing that heat is being carried vertically. This results in a more pronounced upward movement of temperature front, and the advection becomes the dominant transport mechanism in both directions. These differences clearly illustrate the sensitivity of heat transport to flow, direction, and velocity. As talked about earlier, LBM has been applied to many fields. Here, we will do a deeper dive into 3 examples. LBM is not limited to academic demonstrations. It is particularly useful for capturing complex porous scale phenomena in porous media, including multi-phase interactions, slip flow, and diffusion transport. These capabilities make it ideal for simulations in petroleum engineering, microfluids, and environmental modeling. Beyond porous media, LBM also finds application in architectural and civil engineering fields. It helps evaluate wind loads on structures and optimize ventilation systems in buildings. Because of its ability to handle complex boundaries and unsteady flows, LBM continues to gain popularity in many areas of computational fluid dynamics. In modeling aortic valves, LBM is used to capture the detailed behavior of blood flow through the valve leaflets, accounting for both the fluid dynamics and the interactions with moving boundaries. Its localized, particle-based nature makes it well suited for handling the intricate geometry of the valve and the rapid, unsteady flow that occurs during the cardiac system. By simulating blood as a series of discrete fluid packets, LBM allows researchers to analyze flow separation, vortex formulation, and shear stresses. In summary, LBM is a powerful simulation tool that has been applied to numerous fields. It will continue to play a prominent role in fluid simulations due to its easy application and computational simplicity. Thank you for your time.